Hello everyone, I am Debarko Sarkar from Kolkata, India. My presentation today is on atomic layer deposition, commonly referred to as ALD. We take a quick look at the different aspects of ALD which we shall touch down upon in this presentation, a brief journey through the history of development of ALD over the years, followed by looking into the working science behind the technology. We would also see how ALD is relevant to the nanomanufacturing course. A short discussion on the pertinent advantages and disadvantages of the technology would follow, and we would finish off by looking at some of the interesting applications of ALD. So, looking at history, the atomic layer deposition process was first proposed by Dr. Alaskovsky in his PhD thesis published in 1952. He certainly understood the significance and importance of this hypothetical technology and therefore directed his further research pursuits towards realizing it. Under his supervision, Dr. S.I. Koltsov performed the experiments and published the first principles of ALD by the name molecular layering. More than a decade later, Dr. Tuomo Santola and his co-workers developed the first industrially viable prototype of ALD, then called atomic layer epitaxy. This thin film deposition technology found its first applications in TFEL displays. I have put up a few pictures of commercially available electroluminescent displays so that you may relate to places where you may have used them. And then, through several steps of evolution over the past 4 decades, atomic layer deposition is quite an established and widely used technique today. Okay, so let us get into the underlying principles of atomic layer deposition. Here is shown a cartoon representation of an ALD device load lock, and here is the top view of the same. The golden yellow patch within the ALD machine is actually the wafer on which atomic layers will be deposited. ALD occurs by chemical reaction of precursors which are pulsed sequentially. Unlike CVD or other similar deposition methods, the precursors are not pumped into the reaction zone simultaneously. Simultaneous pumping of precursors will lead to reaction within the empty space on top, and then the products would settle on the substrate in a discrete fashion. Although this may be used to form thin films, there would not be good control over layer-by-layer deposition of materials and conformality of the substrate as desired in ALD. As this picture depicts, precursor A shoots out of the left opening and streams across the yellow substrate. This precursor reacts with the substrate and products are formed, which we shall look in a bit greater detail later. The excess precursor and the reaction side products so formed are pumped out of the reaction chamber through the opening on the right. As we shall understand better in a future slide, the precursor becomes excess when the first layer becomes saturated, leading to self-limited single atomic layer growth. This is followed by pulsing precursor B and again pumping it out in a similar fashion. Thus, the entire ALD process can be summarized in this diagram. Repeated sequential pulsing and purging of different precursors lead to formation of the thin film with a precisely controlled thickness of the material to be deposited. Atomic layer deposition is a technique that can be used to provide a uniform or better termed as conformal coating of atomic or molecular layers on different surfaces, including complex 3D geometries, amorphous substrates, nanotubes, etc. Shown here is such a surface, and a cross-sectional view helps us understand about the structure better. These essentially form the capacitor trenches of DRAM. The idea is to conformally coat the surface with some material, such as aluminium oxide. So here we come to a more detailed understanding about the controlled monolayer formation process of aluminium oxide. We start with a silicon substrate which is terminated using hydroxyl functional groups. We pulse precursor A, which is trimethyl aluminium or TMA. One methyl group of TMA accepts hydrogen from the hydroxyl group. A new bond forms between aluminium and the oxygen of the hydroxyl group. Thus, dimethyl aluminium monoxide is formed, while methane forms a byproduct. Similar reactions continue to occur. It can be well understood that if there be N-hydroxyl ions on the silicon surface, in presence of sufficient quantity of TMA molecules, N-TMA molecules would react with them and would thus form a bed of dimethyl aluminium monoxide. And the reaction would stop thereafter. This is the self-limiting nature of the reaction, which helps gain a good control over the layer-by-layer deposition of materials with a thickness precision to its monomer level. The excess TMA is purged out of the reaction chamber through the outlet vent. We then pulse precursor B, which is water. As expected, the water molecule comes and breaks the bond between aluminium and carbon to form a stronger bond between aluminium and oxygen, and methane is again formed as a byproduct. Similar reactions continue to occur till all aluminium methyl bonds are replaced by aluminium oxygen bonds. Water is then purged. Thus the same steps repeat and layers of aluminium oxide continue to form. The box shows the surface reactions in the equation form. The overall reaction is also given. Thus, each capacitor trench now looks like this, a conformal coating of aluminium oxide with precise control over the thickness. And a zoomed out view shows the array of DRAM capacitor trenches in all its royal glory. Note the aspect ratio. It's roughly 15 to 1, greater than 10 to 1, as Professor rightly claimed in one of his videos. This picture is a real image corresponding to the cartoon to its left, a scanning electron micrograph of 300 nanometer aluminium oxide film on a silicon wafer with a trench structure. This picture shows the coated silicon wafer, and this basic ALD process with different precursors and certain different conditions like temperature and pressure can be suitably optimized to coat various substrates like semiconductors, polymers, biological samples, particles, amorphous substrates, etc., with a plethora of materials like oxides, nitrides, metals, polymers, and so on. During the nanomanufacturing course so far, we have seen the application of ALD at certain places, particularly during the transistor manufacturing steps in FEOL and BEOL videos. I would like to highlight some of them, mainly the ones where ALD appeared inevitable to me. Here we are looking at such a snapshot of the screen. Professor was describing a conformal nitride layer for spacer formation, and if I am not wrong, he too mentioned the requirement of ALD for fabricating this envelope. Yet another example on the same video is the requirement of conformal deposition of a thin metallic nickel layer. This is the first step towards the formation of nickel silicide contacts, or what is known as salicide. Towards the back end of the line, we would require a titanium nitride thin layer deposition conformally around the silicon oxide to act as a barrier between the oxide and the tungsten layer to be deposited thereafter. This picture is a 3D cartoon depicting the same. The blue layer on top and within the trenches is titanium nitride, all which looks so familiar after our discussion on ALD deposition so far. As we mentioned earlier, the same underlying principle of ALD is used under slightly different conditions depending on the substrate and depositant, and accordingly different standard methods are widely accepted and utilized today. The most generic form of the atomic layer deposition is thermal ALD. These reactions occur spontaneously at various temperatures. As well known, increasing the temperature increases the kinetics of the reaction, and therefore usually a high temperature is maintained for the reaction to occur properly with low time duration cycles. Metal oxides, nitrides, sulfates, and phosphates are commonly deposited using thermal ALD. However, the same reactions may occur at low temperature as the reactions themselves are highly exothermic. Low temperature deposition is at times required in case the substrate is unable to withstand the high temperature required for optimal deposition conditions, for example for biological samples. In most cases, the deposition rate and quality remains almost the same at low temperatures. But usually, the cycle duration increases as a higher time is required for purging water to prevent thermal CVD from taking place. Some reactions do not take place at low temperatures, or rather would take infinitely long time. Those reactions are enhanced using catalysts, for example, silica ALD. Certain materials, such as elemental metal or semiconductors, are not suited to be deposited by the generic thermal ALD. This problem is overcome using the plasma-enhanced ALD. In this technique, one of the precursors is used in the plasma or ionized form. Often, plasma sources generate hydrogen radicals to reduce the metal or semiconductor precursors. Metals have a roundabout for radical-enhanced ALD, and they can be deposited by different thermal chemistries. These include the fluorosilane elimination chemistry, the combustion chemistry, and the hydrogen reduction chemistry. As we browse through the different slides, it must have been quite evident that ALD offers a number of advantages that are inevitable to be exploited in today's fabrication technology. At different points in the presentation so far, we have mentioned those advantages, but it's certainly prudent to have a summarized look at them. The first and main advantage is the self-limiting nature of the deposition. As explained using relevant graphics, as the atomic or molecular layer becomes saturated at each pulse stage, a highly controlled layer-by-layer growth can be maintained, leading to precise control over the film thickness. Yet another important issue in any deposition technique is the formation of pinholes, which would effectively change the desired electrical property of the device. Pinholes usually arise from localized de-wetting and microbubbles which de-gas during film drying. As is quite evident, such problems are not inherent in ALD because of the unique deposition technique. Third, which is also ascribed to the precise control over the atomic layer-by-layer growth, is a conformal coating of the substrate. Complex 3D surfaces, including particles, biological samples, and high aspect ratio structures, can be precisely ensheathed by a few atomic layers as desired, so that the deposition layer follows the substrate surface contours very closely. Finally, it's a highly repeatable process, which is quite obvious given its worldwide acceptance, leading to its robustness. Also, it is definitely scalable, which means the technique is applicable over a surface area of few nanometers to some centimeters, and there is no hindrance to be on kilometers, so long as the substrate can fit in an ALD machine. According to my perception, while it's true that the advantages overshadow the some disadvantages, thus making it viable and inevitable for specific uses, It is certainly good to take a look at the certain drawbacks for a well-rounded understanding of the technology. Like most other modern fabrication technology, ALD ensues a very high cost, both during installation and to keep the facility up and running. Usually, a typical ALD forms at 100 to 300 nanometers per hour, which is a bit too high compared to other deposition techniques like CVD, which grows at an average of 60 micrometers in the same time. One important constraint as compared to CVD is a relatively less versatility of the process in terms of the availability of precursors for atomic layer deposition of a material, such as nickel tetracarbonyl, tungsten tetracarbonyl, and many alkoxides. The Venn diagram shown here roughly gives an idea about the plethora of materials available for CVD, some of which are also applicable for ALD, while giving ALD an edge only for a handful of materials. We would now look at a few of the important and innovative applications of ALD. Common but certainly important apps include those in micro and nano electronics, such as deposition of high permittivity gate oxides to reduce the tunneling effect for 45 nanometer node transistors and beyond. Other applications include transition metal nitrides like tinitride or tantalum nitride to be used as metal barriers, as has also been covered in this course. Magnetic recording heads are some of the newer applications, while how ALD may be applied in DRAM capacitors has already been discussed before. Biomedical devices made using ALD include coatings of biocompatible materials, polymer ALD, and flexible sensors such as this piece of electronics that can stick to human skin for about 24 hours. Flexible sensing devices to be used in the clothing of athletes to detect movement or heart rate have also been fabricated using ALD. Now, optical devices as applications of ALD. This picture shows a Bragg reflector to be used for X-ray reflection made of alternating nanolayers of aluminum and tungsten fabricated using atomic layer deposition technique. A three-dimensional photonic crystal may be fabricated using ALD. Photonic crystals are structures made of periodic dielectric materials which can modulate and manipulate light so that they are being researched on to be used in future optical computers. This photonic crystal was made in the following process. A crystal array of silica spheres was fabricated. Tantalum oxide was deposited between the spheres by ALD. This was converted to tantalum nitride in presence of ammonia. The silica spheres were dissolved in hydrofluoric acid to leave behind this beautiful photonic crystal structure. Similar principles have also been used in biomedical applications to get an intricate exoskeletal model of an insect to be researched on. Now, towards the end, I note down the references which I have referred to while preparing this presentation. And with this, I end my presentation. I thank Nanomanufacturing course and professor for setting up this wonderful course and allowing me to take this course and allowing me to learn so much about ALD, and I would love to receive comments and reviews from my peers. Thank you.